So welcome back again to the first lecture in this precursor event to celebrate National Space Day 2024. The National Space Day is being declared on 23rd August every year from now on to commemorate the anniversary of the landing of Chandrayaan 3 on the surface of the moon, the first successful space soft landing on the surface by India. And to celebrate this, we have with us a fantastic speaker who's been involved with the Chandrayaan project itself. So I think we are very lucky to have her here with us to talk to us not just about Chandrayaan mission, but we hope also about how she felt like to be a part of this historic adventure as well. Dr. Shyama Narendranath, she did a BSc from Palakkad, Victoria College, and MSc Physics from the University of Calicut in Kerala. She then earned a PhD in 2011 while working on the X-ray fluorescence experiment on Chandrayaan 1. So she's been with Chandrayaan from the very beginning, Chandrayaan has been with her from the very beginning. She primarily works on the composition of elements in the solar system, the abundance of various elements and molecules in the solar system, and also with instrumentation at the Space Astronomy Group of the URSC Satellite Center of ISRO here in Bangalore. So she's the science lead of the CLASS instrument. The CLASS instrument CLASS stands for Chandrayaan 2 Large Area Soft X-ray Spectrometer, and she'll tell us what each word means. The CLASS instrument on board Chandrayaan 2, so she's the science lead for that, and she's actively involved in Indian planetary programs. She's also a trained classical dancer. So she's a person of varied talents and passions and interests. We're very happy to have her here. Somebody who's an integral part of Chandrayaan, has been with Chandrayaan so intimately, to tell us about not just Chandrayaan missions but also the missions of the future. And before we start, I'd like to give her a small yeah, but people might think that I wanted to see what it is. This is a photo of our observatory in Hanway, and this is a book about the women astronomers in IIT. And we also have a set of merchandise for all the gifts we gave you for the quiz. We also have a set for hers. So we also have people attending on YouTube, and so I invite Dr. Shyama Narendranath to give this talk on Chandrayaan, after which we'll take questions from both the audience and on YouTube. So please.
Thank you, Nirish. So I was going to talk about why all this, like we want to go to the moon, and what is that we are going to do in the future. We have this Chandrayaan series of missions. With 1 and 2 we had orbiters, Chandrayaan 3 a grand success, soft landing on the moon. If you have been following lunar landings, you will see that it's only 20 landings so far from 1966 onwards. 66 was the first soft landing, so you can see that how hard this is, and there's only like 4 countries that have soft landing on the moon. So you can pretty much understand how important this landing was for India. And what does it, like it shows our technology, where we are in par with the global standards. So we also want to appreciate the fact that why we are doing this, why do we want to go to the moon, and what's the prospect for it. The moon is such a familiar object in the sky, nobody needs an introduction to the moon, right? You see this every day in the sky. And no wonder there's been a lot of fiction written from 2nd century AD, I understand, on going to the moon, having aliens there. So there's always been the question of what is the moon made of, can we live on the moon, what would be the environment like, are there people on the moon?
People online can't hear you. Where the mic is?
Would that be? Yeah, you can tell me in case. The first actual landing on the moon happened in 1966. This is a USSR mission, Lunar 9, and that's the first ever photograph after landing. You can see how different it is from the Chandrayaan 3 photos that Neeraj had showed. This is very, very early. This is 1966, but that's a remarkable feat. Before that there were several missions that went there and really crashed. Because what is the difficulty in doing this? you need to also appreciate the fact that when you launch something from Earth, it can go around Earth. We have several satellites, right? But now what you have to give it is the velocity to escape from the gravitational field of Earth, go with the right velocity so that you can be around the moon. The moon's gravity field should capture it. Now, you see Earth is moving, moon is moving, the spacecraft is moving, so you need to make the right calculations to be there. See, I launch it today, it has to be, moon has to be in a particular position in space at this point in time, and our spacecraft should be there at that time, right? Because it's such a very crucial calculation. You miss that, you either slam on the moon or you are just lost in space. So there have been dozens of missions that couldn't really go around moon in the early 60s, and they all just crashed on the moon. So therefore, just going around the moon itself is a very challenging task, and what you need to do when you're doing maths in school now, like this is just purely a mathematical problem. You have masses, right, and you need to just calculate how exactly, for which you also need to know the gravitational field of the moon very well. As you now go around the moon, you understand that you cannot just consider moon as a single point mass. There are ups and downs as you go around the moon, because it pulls differently as you go around the moon because of mass concentrations. So you need to know how the gravity field of the moon so very well. That's when you can really land on the moon. And of course, everybody involved knows Neil Armstrong. Who are the other two people? Buzz Aldrin and Michael Collins. So Michael Collins was in the crew module which orbited, while Neil and Buzz Aldrin landed on the moon. And I just read in a book that before we went, Neil Armstrong. So that's all planned, right? Like they don't decide. This is like every step is planned. Before they go itself, they plan how you should do. Who should put down the ladder? That's all very well planned. Before they went, the US president asked, "Are you scared that you will die in space?" And apparently he answered that I'm worried about dying in space, but my irrational lust for bizarre, faraway rocks is stronger than my fear of exploding. That's the kind of incredible courage that they had. You imagine you're going to moon, and you're not really sure whether it's a one-way ticket, isn't it, sir? It's said that US had 2 letters written for the president to read out the next day. One, if they are successful, congratulating them, and what we actually all read. And the other one, because they all prepared this, right, beforehand. And was if they died, what to say if they died. So imagine the kind of courage they had, going up there. And it's whose footprint is this? No, it's actually Buzz Aldrin's. So if you go into this website where there's a history recorded, you can see in Apollo 11, which is the first landing. In fact, for all landings, each image who took. So this was an experiment. They wanted to see how much would their boots go in. You know the weight of your boot, you know the weight of the person. So when they press, what force do they give, and how much can you really press into the lunar soil? So lunar soil is very fluffy. It's not just them. After this, there's been a total of 6 human landings on the moon from 69 to 1972. So in each of them, 2 people walked. So totally there are 12 humans who have walked on the moon so far. And they did a huge variety of experiments. And one of these things was to see what the soil is like. And as we know now, this is a very fluffy kind of soil. There's static charge. It's very abrasive. So when they came back, they looked at their suits and could figure out that they're really sharp soil-like things. Beyond this, there's been many robotic missions. There's been a lot of USSR missions also robotic in those times. And what is marked here is all the locations where there is some human object. So you can see that this is the near side of the moon that we see from Earth. You must be familiar with how the moon looks like, right? These dark areas that we see from here, And this is the far side, so there is no dark side to the moon. It's always, there is sun. We say dark in the sense we cannot see it from here. So it's more appropriate to call it far side. And the dark is only in the sense that we cannot see it, but there is sunlight there. So if you go on a spacecraft with a camera and go around the moon, so what do they typically do in a remote sensing? You have the moon and the satellite is going around and the moon is rotating underneath naturally. So then every time you go in an orbit, you're seeing a different part of the moon. So in that way, you can globally take pictures, and that's how these pictures have been taken, with several such orbits around the moon. And what is the first thing that you see? It's very different, right? The near side and the far side seems to be very different. These dark areas here, which are called mare. Again, mare means sea. So here there is mare imbrium, mare tranquillatus, all Latin names. Because when first with telescopes, Galileo Galilei, he was the first one to really very systematically look at the moon, taking years of diagrams. He figured out these are smooth plains, and there was a possibility that they could be, mare means sea, they could be seas. So it was named like that, and we still call them, but today we know it's just a result of volcanism on the moon. So these are basalts. You know the magma that comes from volcanoes. There are no volcanoes on the moon as like on Earth, but there is volcanism in the sense there was hot magma, liquid magma at some point as moon evolved, and those have come to the surface, and that's what we see as these dark areas. So most of our landings have been on the near side, because if you go to the far side, you cannot directly communicate with using radio wave communication, right? Because in most landings, we want to keep track of what's happening on board. You know, you get every 3 seconds data, and it will be like nail biting to see whether it's landing, etc. But if it's on the far side, imagine for a long time you can't do anything about it, or you can never do about it because you cannot communicate with the spacecraft. So, but these two here are from the Chang'e missions, which is the Chinese missions. So they have a satellite which is parked on the other side of the moon, so that from Earth, so it's called the L2 point. So it's the L2. So we spoke about the L1 point, which is the Sun-Earth L1 point. Similarly, Moon-Earth also has these L1 points. Because Lagrange points are simply points where it balances the force of gravity. Right? So every two bodies will have. Is there gravitational force between you?
Yes.
Yes. So in principle, you can calculate this for any ray, right? Chang'e landed a spacecraft on the far side of the moon, and they could communicate because they parked a satellite on the other side, and they do the relay from there. So you can see most of the landings have been in the equatorial side of the moon. So this is somewhat the equator part of the moon. That is because relatively it's less challenging. As you go further down towards higher latitudes, the terrain becomes difficult, the communication becomes difficult, you cannot always see that illumination. Primarily, the sunlight becomes fainter and fainter. And because of that, most landings have been here. So that's where Chandrayaan 3, it could land in a high latitude region, almost 70 degrees south, this point here. So that's one of the things, again, with Chandrayaan 3, that you could come down and with a high latitude. I'll come to why we are moving towards the South Pole, because that is a destination everybody wants to go to. So now we want to understand the moon. What are the things you typically would want to know about an object? What is the moon made of, right? So obviously that's the first question early on when we started looking at moon that everybody asked. How fast is it moving? Was it always there? Because it's a satellite of Earth. Will it go away one day? And what is the connection between Earth and Moon? Or is there any connection at all? Are moons common? Because now, today, it's not just about our solar system. There are more than 5,000 planets discovered around other stars, and we know every star inevitably has planets around it, which means there must be a lot of moons also. So the search is on to find exomoons as well. And as we know today, is there something about moon to do with life on Earth? So these are all possibilities, and hence it's not just about our moon and Earth or our solar system, it's also about solar systems out there in the universe.
What is special about the moon is that look at the inner solar system. You know these planets, right? None of them have moons. So it's only Earth that has a moon. So doesn't that make it special? So that's again written here. So it has Phobos, Deimos, but they are not really a moon of Mars. They are asteroids, yeah, and they were captured at some point. Yeah. So that's a difference. Because for moon, we know that it formed along with Earth. It's as old as Earth, and so that it's been a constant companion. So that's why we call it a satellite of Earth. Whereas even Phobos and Deimos are going around Mars, but it's going in such a way that one point millions of years later it's going to slam on Mars. So they were just captured sometime. So there's a difference. So that makes it very special. How did only Earth get a moon? You look at Venus, it's almost the same size as Earth, and it's also chemically very similar. The composition is almost same as Earth, and still it doesn't have a moon, and none of the other planets have. And it's again special because then you might think, right, Jupiter, we said, counted the number of satellites of Saturn. I mean, they all have moons, so we could get one like that. But if you look at the size, Jupiter is like 1/100th of the size. The satellites are that tiny, about around these giant planets. If you look at Moon, it's almost 1/4 the size. So we have a big satellite. So it's very difficult to explain. It's very difficult to explain how we got a moon by normal theories that applies for the outer solar system planets. So for the Jupiter or Saturn, it's generally believed that the leftover material which forms a disk around it, in fact you see the rings still, right? From that coagulated or accreted rocks and dust, and those become the satellites because they are tiny. If you do the right physics and maths, you can prove that they formed from that leftover material around these big satellites. But for Moon, it's very difficult to say that because you can't make such a big moon out of the leftover material from the Earth's formation. So there's a problem there, and Moon is special in that way. In the entire solar system, Moon is the only body which nothing much has happened on its surface. That makes it extremely important. So you look at these craters. So craters are a record of impacts. So crater is just a deep pit that's formed because something slammed onto it, like asteroids hit. So very early in our solar system, it was very chaotic. It was not like now. It just formed. There's a lot of dust and gas around, a lot of small bodies, rocks. So there were a lot of collisions, and those times, probably all planets were getting slammed and impacted by these kind of rocks of various sizes. Now, Earth has changed, right? We don't have any memory of what happened that 4.56 billion years ago. Look at these craters on Mars and Venus. Even you don't have the record of that old craters even on them because things have changed on the surface. Mars, this is carbon dioxide ice in the Mars, one of the craters. Its surface has basically changed from its original surface, and this is on Venus. Again, there is volcanism on Venus. Actually, very young volcanism. It was in the news that Venus is very volcanically active even a few million years ago. Which means here, this is basically the magma that's flowing out of a crater after a collision. So Venus has resurfaced, or the surface is not the original surface when it formed. So you basically have no way to know what happened long back. So we really repainted the whole place. And that's Earth. Do you know where this is? This crater is Maharashtra. So that's a Lunar crater. So again, that's a place to go to, but it's not an easy trip. But that's where there's a crater from, I think, 60 million years old or so. And there's even there's a scientific proposal that says this is the one that killed the asteroids. This is the one that killed the black holes because the age-wise. Whereas you look at the moon, this is a crater on the moon. Nothing much happened from its initial impact. So what you see is actually a record of. So it's like a newly painted wall, and you keep hitting it with rocks, and it's just there. You never repaint it. That's how the surface of the moon is. You have record from 4.56 billion years ago to until now. So that's an incredibly lot of information that we have about the solar system, how solar system was at that point in time. You know, all those records of the hits are on the moon. And as I said, there's this big difference between the near side and the far side, which is again an open question. Like we really don't know why we see most of these. If you think that these big impact basins, so when it's a small thing, we call it a crater. But if it's a big impact, it makes a big basin, and then molten lava fills it in, and that's how these are formed, and we call it mare. But on the other side, you hardly see anything that kind of features. So one of the reasons we think, and again, this is a Tycho crater which you just see with the naked eye. So if you haven't noticed, next time you look at the moon, look at this crater here, you can see these ejecta. So this is like a splash. Now you can imagine, right? This is a very circular crater, which means the splash might have just come up. So craters are also, just looking at the craters tells you something. And if it's an elliptical, the impact must have happened at an angle. If it's just circular, it's coming from the top. So it actually provides a lot of information. And you see these crater has rays. You can actually see the splash. So it goes halfway across the moon, which means that velocity must have been that big. So there's a lot of information you can gather by just from such a photograph. One of the basic things after the Apollo missions that we could figure out was that this difference in color that you see, it's basically difference in composition. So they are really made of different materials. Just to give an example, this is the amount of iron. You have iron in the soils, right? The Mars surface is reddish because of the formation of iron oxide. That's where you have a red Mars. In the soils here also we have iron, but lesser amount. And on moon, if you map how much of iron is there on the surface, you can see such a big difference. So these are all those dark regions that we call mare, which seems to be having a higher iron than the rest of the place. So it just tells you that these are basically two different materials. So now we know that the darker regions are basalts, just like we get from the volcanic basalts here. And the rest of the areas are made of primarily a mineral called plagioclase feldspar. We'll probably learn about rocks and minerals in your school. So while basalts are igneous rocks as a result of magmatism, whereas the other one is not. And we also find that the crust on the far side is thicker. So yellow is thicker crust and the blue is thinner crust. So that's also probably one reason that those kind of big impacts did not really dig deep enough. You look at Tycho crater, the crater that we have. If you look at it if you just look at a black and white photograph of the moon, you don't see much. So when we do a scientific study, we have to look at it in different. Just like if you use an infrared camera to look at your body, you see it differently, isn't it? That tells you your temperature. You might have looked at infrared cameras. Similarly, when you look at it in different wavelengths, you get to know different features of that object. So in Tycho crater, if you look at it, you see the composition of these ejecta is different than the rest of the place. Right? That also tells you it has excavated something from deeper and thrown those material around. So the blue is different and the purple is different. This is the rock abundance here. You can see the floor of this crater has higher abundance. Just around it is higher abundance. The temperature is different inside the crater and outside. And this is about roughness, like the grain size that you have there. The temperature also tells you that this is a young crater, that the energy of the impact still remains there. So the basic question is what made the moon? And it's not that we are asking this question now. It's been from since humans have walked on Earth probably, and in every mythology, in fact you just do a Wikipedia search, it has a list of mythological characters associated with the moon. Because moon is a timekeeper in almost every culture. This is something that we use, the 28 days of the moon waxing and waning is something we really use for a calendar and time. So the primitive human beings, almost as 40,000 years ago in cave art, moon is being depicted. But the first rational thinking on how moon was made was done by George Darwin. So he's the son of Charles Darwin, the evolutionary biologist. He said that probably moon was torn off because Earth was spinning very fast, and something spinning very fast, and if it's partially molten, you could tear off a piece of it. So that's how probably the moon is formed. Harold Urey is famous for the Urey-Miller experiment. You've read about the Urey-Miller experiment. He tried to, in a glass jar, recreate the soup of life. So that's the famous experiment that he did. And he said that probably it could be that moon formed somewhere else in the solar system, and just like the Mars asteroids, Phobos and Deimos were captured, maybe this was also just captured. One thing I always want to point out is that it's not that they are astronomers, such that Harold Urey was doing biology experiments as well as thinking about this. So the scientists of those times were not at all compartmentalized, right? You just like they're free thinkers. So that's one lesson we need to see. Is because you are a physicist, I'm not going to worry about what happened in biology. But they were like really free thinkers, like Newton. What all didn't he do, isn't it? So probably Urey was also one of the kind of person like that. So what do we do in a scientific theory? You make a story, isn't it? You have to make a story. You have to be really imaginative and make a story, but based on facts. That is the scientific method. So what do we have to first make a story? You should look at what is there. What do we know about the moon? So very simple facts. The moon is moving away at the rate of 3.8 centimeter per year. So every year, the distance between Earth and moon is increasing. So what does that mean? That long back? Yes. It was closer back. Right? That's very simple to say.
It means centrifugal force is overwhelming its centrifugal force. By much more.
Centrifugal force?
Centrifugal force is slightly overwhelming its centrifugal force.
So it's basically a transfer of energy, right? Because the total angular momentum of the system has to be conserved. But you look at it simply, what does it mean? That when you can follow the motion of this, you know that every year it's moving away, the distance is increasing, which means if you trace back, that's the point we want to see, right? We are looking at how the moon originated. So one of the things that you can think of from this perspective is that moon was
It might have arisen with the Earth
right.
itself.
It was certainly closer than before, at least, right? And moon has a lower density than Earth. So after Apollo missions brought back and the Lunar missions brought back material, one of the things very obvious was that the density is lower in the moon rocks, which means that the core of the moon is very small. So most of the density comes from the bulk density. If you take the whole planet and do a mass by volume, assuming it's homogeneous, you can very simply calculate like that. If you do that, the density of the moon is much lesser than Earth, whereas one by like 30% of the density of Earth is in its core, whereas for moon it's like 1.5%. So the core of the moon is very small. Moon rocks does not have water, so that's again one of the first things we found. Like any terrestrial rock, anything on the Earth has water absorbed into it. It's very difficult to make it absolutely dry, whereas the moon soil is very, very dry. You would have read a lot of news on finding water on the moon, but we are actually talking about parts per million, ppm. That means you have a million molecules, like if you say 100 ppm, that means 100 of them are water. So it's actually that low that we are talking about. But even that's a discovery now, because what we originally thought that moon was absolutely dry. And moon is as old as Earth, which means we have ways to really date moon rocks, right, when they were brought back. And so you can do radioisotope dating, and what we can find very precise ages for those rocks. And the oldest rocks says that it is really 4.56 billion years old, which is the age of the solar system, which we know from primitive meteorites, really. Actually, the age of the solar system is really determined from a particular kind of meteorites, which are the most primitive material we have in the solar system. And so, if you compare moon was as old as Earth, which again means that it formed almost at the same time as Earth. So these are just clues. We just put down some basic things that with this you can think of that, okay, moon was closer, moon is formed, it's as old as Earth, so it formed at the same time. So therefore, the formation of Earth and moon must be connected closely. And the origin of the moon, as of now, we think is this, that a Mars-sized body came and, this is a simulation, so basically they do numerical simulation. You can see that there was a Mars-sized body which hit Earth, and then whatever that smash threw away particles from matter from Earth, and they accreted to form the moon. So that's what we think now, because this is the theory that most fits the observations that we have today. Again, there is a debate on when exactly this happened. Is it after Earth really solidified? Because there are differences also. Now, if you think of this means most of the material of the moon could be from Earth, but there are stark differences that tell us that moon's composition is not exactly like Earth. So you have to also account for these differences. So to fit in all that, what we think is most of the matter is coming from the impactor rather than Earth. So that makes the story right. And what happened soon after the moon formed? This is what we think. So this must have been a giant event, right? It's like a big, now you always talk about near Earth asteroids, whether they're going to hit us. That's going to be a, it would be like a threat for Earth. No, everybody would, that would be the end of Earth if a big Mars-sized body now hits us. So this is an energetic event, and what happens to all that energy? It's stored as heat. So at the beginning of when moon formed, the moon was probably entirely molten because of the heat it acquired from this impact. And then what happens? So that's it. That's its total amount of energy, and now it has to start cooling. So as it cools, materials condense, become solids according to their condensation point, right? So there are metals like, say, aluminium, which has a 1200 degrees Celsius or so as its boiling point. They will become solid at a certain temperature, and then as you get cooler and cooler, other materials become solids. So that's what is happening here. And when the first solids came, the rest of the material was still molten. So what happens? They floated up, and heavier metals sank to the interior. So that's how the planet or the moon differentiated. And we know today that the crust of the moon, which is a kind of white, that's the white rocks that we see, the white highland areas that we see, the bright regions. It's made of a rock called anorthosite. And deeper down, there is a mantle, which is mostly consists of these minerals, and then there is a metallic core. Now, minerals are a very, it's like very interesting to study minerals because they not only tell you what the composition is, they also tell you what is the environment that made it. Just to give an example, if you take diamond and graphite, both are carbon, right? So if you just want to know what is it made of, it's carbon. But do they have anything in common? Just the fact that they are carbon. So when you find a diamond, you know that it is formed in a high pressure scenario, right? It has to be deep inside the earth where those pressures. So see, getting some rock like that also tells you what is the pressure in that environment at that point of time. So you get so much information by bringing a sample back from Earth. And that's how, in fact, most of what we know of moon today was really laid out. So what is the source of information that we have today? We have 584 lunar meteorites. So meteorites fall on Earth all the time. Small ones just burn in the atmosphere, but a lot of them also reach the surface. Just that it's not very easy to pick a meteorite in this kind of normal scenario. So usually meteorite search is done in Antarctica, where it's white and it's all ice, so it's easy to see a meteorite, or in deserts. So there are like Antarctic meteorite searches, teams that go and look for meteorites. Isn't that an exciting job in itself, like going to Antarctica and looking for meteorites? So we have 584 confirmed lunar meteorites, and in fact, all the information about them is in those links. It's like out there, anybody is interested, you can just go and check it out. The return samples. Apollo brought back 382 kilograms of material. Lunar, which was the USSR missions, which were all robotic. So to also appreciate that in the 60s, when humans landed, but USSR also had robotic missions where they brought back samples at the same time. They brought 320 and the Chang'e 5 and Chang'e 6, which came back in June, very recently. They both got 1.75 kilogram each. Then we do in situ measurements, like Chandrayaan 3 had a rover, so you put instruments on that, they go and do in situ. So that will be, we call this in situ measurements from the lander and rover. Remote sensing from an orbit, that's still useful because how many rovers can you send, right? And when you send a rover, maximum you can look at maybe a few kilometers. You cannot cover the whole of moon just by doing that. So you do need orbiters to completely look at moon globally, and that's what is done by remote sensing and using ground telescopes. Still, even with, just like Neeraj showed, optical telescope, there is also GMRT which is being used sometimes to look at the moon. We have used Gauri Bindu to look at towards the moon. So, still ground telescope. So, each of these are complementary measurement. You shouldn't think that once you send some instrument in space, that means there's no point in doing a ground measurements because technology levels are different. But it's all very complementary. You can't do a long-term observation with a space telescope. These are short missions. So we have to do the most important thing that we need to do. You have to do the thing that can be only done when you are on the surface of the moon. So that's how you will choose experiments to fly on these missions. That's a very nice panoramic view. So all these return samples came because from the Apollo missions where they walked. In fact, by Apollo 17, which is the last moon mission, they had a road to 10 to 12 kilometers away. They had vehicles like this. They used them to drive. And the samples they brought back, to give examples, in human missions, you had pretty large rocks that's brought back. And this is from Chang'e 5, which is a scoop soil. And in magnified version, you can see the small particles in that. This is so moon soil is very special, because on moon there is no atmosphere. So the micrometeorites that keeps falling, the solar wind, the particles from the sun, all of these are continuously landing on the surface, which means that very small scale there are always impacts. So this energy goes to the soil, and in fact very locally they melt the soil and make kind of coagulated material. So that's what you see here. So this is very unique to the moon because it's an airless body, which doesn't happen on Mars, for example. So and these are glasses. So again, this was very peculiar. It is green glasses. You see moon as black and white, and it doesn't need. There's no color on the moon as such. But when Apollo brought back samples, some of these had these orange and green glasses. So again, what's the difference between forming crystalline material and a glassy material? It's in the time it takes to cool down. So when you find something glassy, which means it cooled very fast. It didn't get time to make crystals. Whereas if it's a rock is very grainy, that means it cooled very slowly. So it could form big grains. So that's why geologists do an amazing job. Geology, I feel, is more, it's like a job of where you need the wisdom. Just by studying the textbook doesn't help. You actually need to have years of experience. It's like doctors diagnosing. With years, you get that experience of saying what more about what you find. And I know if you go on a geological field trips, you can see how they would pick up rocks, and you can almost tell the whole story of the place by looking at a rock. And that's why in Apollo missions, initially they had all those from the US Air Force going in, but they took a geologist in one of the missions, and he brought back very special samples which included these green glasses. And they, not just the surface, they also dug up to 3 meters and brought back the cores to see what lies underneath. It's very, very difficult to make a drilling on the moon because the torque that you need to apply is very different. And you can't even test it in the same circumstances because the gravity there is 1.6. It's a vacuum, so it gets heated up faster. So imagine the drills that you use here. You just cannot use them there. So the design itself is very different. And this is how many of these cores have been there. Just another thing I wanted to say is that they did bring back we said Apollo missions, for example, are like 382 kg brought back. So it's not that they brought it back when the last one was in 1972. But it's not that they just opened all boxes and started looking at it. No, they had the vision that technology is going to change. There are younger people, there are future generations to come. So only one-third of the whole thing is open so far. The last one was opened in 2019, and they do give out an international call for proposals. Anybody who has a good proposal to say, this is what I'm going to do with the sample, it will be given to them. So this is, for example, the latest, it's an X-ray CT scan of a rock. So earlier you had to distract the socks, you have to slice it to see what's inside. But with new technology, you see you can just do a CT scan of the rock without causing any damage to the rock. So that's the kind of technology we have today. We're using it on something that's brought back from the moon in the 70s. And again, all these images, and there is this policy, even as scientists, when we do, it is like anything that we do, the data has to be in an open source. So even if you don't have a facility of an X-ray CT scan, these images are archived, just like astronomy data. It's there, and there are like high-resolution images through microscopes, all archived. That if you want to sit in your lab and study Apollo samples today, we can do that. So some early revelations, which I already said, but is that moon is an evolved, differentiated body. So what does that mean? If you look at asteroids, they are not differentiated. In the sense they don't have a cross-match code differentiation. They are homogeneous bodies. Some of them are just rubble piles, but whereas moon is like a planet. So studying moon also, help us understand how terrestrial planets evolve. Because it's like a planet. It's just that it's going around Earth, but it's almost like a planet. Moon formed magmatically hot, because you see magma there, look at the kind of rocks it has, you know that it formed in a very hot environment, which means there was volcanism on the moon. Not the kind of volcanism we have on Earth, definitely, because ours comes from the plate tectonics also that we have, right? And so moon doesn't have mountains of that kind, but there are elevated areas as well. Moon rocks are older than Earth's. What it means is that Earth, we cannot find that an old rock because of the changes that have happened on the surface of the Earth. But on moon, we can really go back in time, and it's formed in a very anhydrous environment without water. Moon surface is covered by a thick regolith. So the soil on the moon is a result of the crust being bombarded continuously 4 billion years. Now imagine rocks and asteroids and now small meteorites of micron size to centimeter size constantly bombarding the surface. So what you see, the soil on the moon, is a mix of all these things. That's called, regolith is just the name for unsorted soil. Even on Earth you can call this regolith. Moon does not have life. So first thing, Apollo 11 and 12, they had quarantined the materials and the astronauts because there was this possibility, we don't know, right? But after that, it was like moon's environment really is not conducive to life. So we don't think there is any possibility of living things there. One of the things, there are so many things from Chang'e 5, one of the things that the Chang'e 5 basalts found was that moon was active as recent as 2000 million years. Now what is the problem with this is that, see, you had a big impact, you formed moon, so there is a certain amount of heat in that body, and it's cooling. Now you don't have any other way of giving it extra heat. But then if it was active as recent as 2000 million years, where did it get the heat from? So maybe the point where we decided, how it's cooling, either the composition inside is different, or why is that cooling rate different? So we don't know that yet. So that's one of the important discoveries that from the Chang'e 5. I'll just glance through the Chandrayaan missions. Again, as I said earlier, we absolutely thought there is no water on the moon. Now, why water on the moon is so important? Because that's driving the whole world towards moon today. Because if there is water, that means you can set up a permanent base. So the exploration of the moon basically comes from the fact that there is water on the moon that can be extracted. And Chandrayaan 1 was one of the reasons that it was discovered that it's not just the polar regions of the moon, but globally there seems to be water on the surface of the moon. And this probably is not coming from inside the moon, but it's a particular reaction that happens on the surface because of solar wind interacting with the surface layer. And what do we see? So this is a remote sensing experiment called Moon Mineralogy Mapper that was on Chandrayaan 1. It was an instrument coming from Brown University in the US. And what was it looking at? It was just looking at the reflected sunlight in the infrared. And you know water molecules? So those who were in the high school will remember this. The water molecule is like this, right? And it has these three kind of bending that can happen. So when it has to stretch or bend, there is a change in energy that is needed. And according to that, there will be a signature in the spectrum. So the spectrum is basically, if you histogram or you plot wavelength versus reflectance, and see this dip here, that's coming because of the one of these modes of vibration. So you look at this and figure out that there is a OH bond on the surface of the moon. From the same instrument, earlier we said there was no such minerals on the moon that requires water to be formed. Very different in the case of Mars, because in Mars we find clay minerals, which obviously have to form with flowing water. So you know, on Mars there are sedimentary rocks. So all this shows that Mars had water in the past. Well, Moon, nothing of that sort was found. But then from Moon Mineralogy Mapper, you found that at the higher latitudes of the moon, there is a mineral called hematite, which again requires water for its formation, which was a surprise. And Chandrayaan 1 also mapped the moon, basically composition-wise, mineralogy, and this is class on Chandrayaan 2, which is doing. So each of these tracks is, how do you do this? So you are on an orbit and you have your camera pointed towards the moon, and as it goes, this is a track that it does, right? And so you're covering the moon like this. Just to give an example, this is a very high resolution map on Chandrayaan 2. So this is a mare cretium, one of those mares with basalt inside, and outside is this anorthositic white rock. And the different colors indicate that the composition is different. You see a very dark region here, reddish, which means it has a very high amount of magnesium. Magnesium is a very key diagnostic to look at magmas. Magma source can be different according to the amount of magnesium it has. So this is just to give an example. With Chandrayaan 2, we are able to make such very high resolution maps, which is very new of its kind. The Chandrayaan missions also mapped globally the moon in 3D. So you can see one of these craters. You see a 3D picture, right? How do you take a 3D picture? You have to have three angles. So it's a stereo camera. So it had 3 cameras looking at the same place in different angles, and merging those images, you can make a stereo camera. So you have a whole moon map like that. This is again Chandrayaan 2, very high resolution images. You can see these boulders. So this camera was used to decide where to land on the moon. So that's why this camera was built in the first place. It could work in very low light. So it could work at 6 degree illumination and lower. 6 degree is what? It's almost grazing angle. Right? Because we wanted to go to the south polar regions where the sun is always at grazing angles. So this camera therefore was a faint light camera. And you can see that the smallest that you can see is a 25 centimeter. And the next picture, it's Apollo 11, which Neil Armstrong came down and imaged by Chandrayaan 2, which is 100 kilometers away. Imagine like you're looking at an object from 100 kilometers away, which is as small as 25 centimeter. So imagine the kind of camera that is. So this is the decade of return to the moon. There are 150 missions or more that's planned worldwide in this decade to the moon. So all this is because the future at the moon, at the South Pole, we think that at least maybe in the next decade, humans can land again and can have permanent bases. So that's the whole idea of everybody going to the moon. And in Chandrayaan 3, this is how we went to the moon. Again, there are different ways to go. Basically, you do have to leave Earth and then get captured by the moon. But like Chandrayaan 1 went in 5.5 days. So it's according to how much weight you are carrying, how much fuel you want to use. That's how it will be decided. So when humans go, we want to go obviously very fast with smaller timeline. But here we used a very nice technique where you use the Earth's gravity itself so that you can conserve fuel. So you did a bigger and bigger ellipse around Moon, and at one point when the velocity was, because if you want to leave Earth at this point, you need a higher velocity. You have to give it a right. That's right. So it just takes longer, but in a robotic missions like this, it's fine. When it's human, you don't want to spend a long time in the radiation environment. So yes.
Slingshot images is also used for the Voyager missions to move further out in space.
Yeah. So this is called gravity assist. Right. That is the technique used. So this here, the number of Earth burns that you have to do, conserving. So there are a lot of things here, not just about gravity assist. You have to look at how much fuel you have, the size of your tank, when exactly to burn this, what rocket you use, which will place it in the first place, in which orbit. So this calculations will be very unique to that particular mission. And so this was done, and as I said, you do trajectory correction on the way, and then again it was like you first do an elliptical orbit and then come down, and the lander and the orbiter, there was a propulsion module, it was separated, and then touchdown happened. So this was the area that was planned. So it was pre-designed that we looked at the most probable areas on the moon where it can land safely. Now what is safe landing, which means because the rover has to move, you also have to look at the slopes, so it has to be less than 15 degree, for example. The illumination has to be 6 degree or around that. So it's very constrained. You can't just go and land anywhere, anytime. Because the illumination also changes, and that also constrains our landing day. So if we don't land on 23rd August or the next one or two, you keep losing the days. Now on moon it's 14 days sunlight at a particular site. Therefore we landed, I think we had 10.5 days to land on the moon from that point of daylight. As you shift, you lose your days. So everything is so constrained. Imagine the site that you want to be in, the illumination there, everything matters when you want to design a land. So this was the area. Anyway, this video was already there. So that's the first photo, and that's what the landscape looked like. It's quite different from the other images that we have from the Apollo sites. And again, this is the first time we have such a close-up view of a very high latitude region. The terrain looked different. There were plenty of photos in image gallery in ISRO, but again, that's the lander taken from the rover, and you can see this kind of boulders. You see the size of this matters while landing. What if your lander leg was on this? It will topple, right? So, it's very important we know the number of boulders in that site. And with cameras on a 100-kilometer orbit, you could only look at something like 25 centimeter. 25 centimeters itself is big. So as you come closer, Chandrayaan 3 also decided that it had this capability that you first take images and decide whether you want to land here or you want to move ahead. But fortunately for us, the first site itself where it was hovering was fine. That's where we landed. So what next? The destination is the South Pole, because that's where we know there is water, though we don't know how much or whether it's deep inside or mixed with the soil. So when you say South Polar region, it's above 70 to 75 degree. And how difficult this terrain is. This is sunlight in 2024 in the South Polar region. Because the moon's axis is not tilted like Earth's. The sunlight there is always like grazing. It's like the maximum is 1.5 degree. So which means it's like a twilight time. So always it's dark in that manner. And this is how the shadow is moving. Also because of the topography of the moon, which means there are these highs and lows. It casts long shadows. So imagine how difficult it is to find a place here to land. So when everybody wants to go there, we also have to find sites where, see this site for example. When you landed, it might be in sunlight, but then it looks like it soon gets into a shadow. We don't want that as well, right? So this is the challenge in going towards the poles. We went up to 69 degree, but now going further is also very challenging. So with the technology for a future mission. This is really, I mean, it's not really because the science fictions that have been written, you see in the 19th century is true now, right? Going to the moon is true. Then we are very sure that maybe 30 years from now, you probably have something like this there for some of you to be working on this. And the prospects, there is a lot of research going on for in-situ resource utilization, which means we cannot carry everything from here. No? If you want to build something like that, that's going to be economically very difficult, the cost, etc. So you want to build with what is available there. That's called in-situ resource utilization. In fact, there is 3D printing of lunar simulants being pursued. It is to basically get oxygen, water, hydrogen, etc. from the moon itself, take the metals from there. So that is where the world is going ahead for. And in fact, the Chang'e 4 mission had cotton plant seeds sprouted on the moon. So again, lunar farming is also not science fiction. It's going to happen. And there is a leaf experiment in Artemis 3, which is a NASA mission in the future, where they're going to take some seeds and see how it goes. So we have a future too, because one of the most challenging things to do was to show that we can land safely on the moon. It's just AI generated. But one of the most, that was the most major milestone, right? And we have done that. So definitely we have a future too. And so that's probably what the far future is. Who said this? Buzz Aldrin. When he landed, everybody knows what Neil said, but Buzz Aldrin said magnificent desolation, and there's a book by that name. But looks like the future of the moon is going to be that. Thank you.
Thank you so much, Dr. Shyama. I think hereafter, when you look at the moon in the sky, when you go past more, you look at it a bit differently after today's talk, because you can relate to it in a few more ways than you did before. Right? You know a bit more about its origin, about its science, about what it's planning to do. I think we're planning to do that. So we can take questions now, both from here and YouTube. First, we'll take questions from here. So just put your hands up and call. Yeah, the person with that. There'll be mics. Please speak into the mic so that people online can hear your questions there.
Thanks for the session. Can you please show where we landed on the moon in the South Pole? Slide. It was so quick we couldn't.
Oh yeah, sorry. So it's 69 degrees south.
Right, where everything was there. Yeah. So it's 69 degree 32, roughly 32 longitude. So.
Yeah.
So here.
Near the typo.
No, much lower. Tycho is here,
Okay.
much lower, very here, only 69 degree. So that's why it's very different from the rest of the questions.
So one more question. Titan is a moon or?
Can you speak into the mic?
Titan is a moon, yes.
Okay. Thank you.
Thank you. Yeah, the person on the right at the back, please.
So, thank you, ma'am, for the session. I have studied that there is nodal precision at the moon, like the nodes rotate with the plane of the Earth, and that's around 8.85 years. And the orbit of the moon is also tilted with respect to the orbit of the Earth around the sun.
Yes.
So basically, what I wanted to know is the rate of the tilt varies. So at what rate it varies, or what duration it completes the swing?
The precision that it has.
Yeah, means the tilt is around 5.1 and it can vary like 4.9 or 5.1. So
I don't know the exact number.
means at what rate or something like.
Oh yeah, I don't know that
Okay.
number. Yeah.
The precision is 18. The period is 18 years. I don't know about the
The rate
variation.
is asking.
The rate I don't know, but the period for one full precision is 18 years, which is also why it's the Saros cycle, which is why eclipses have a periodicity of 18 years because of that as well.
You should
that can
probably
look it up.
calculate.
Yeah.
You should probably calculate that.
Sure. Yeah.
But for it to come back to the same actual angle takes 18 years, which is why the Sara cycle eclipse periodicity is also same. Yeah, please.
My question is like, why are there no more human explorations now?
Okay, that's more of a, yeah, it's not a technical question. I was also not there at that time, but what I understand is probably at that time there was a lot about technology development that will raise your country's level. So you know about the Cold War and how USSR and the US was really raising to the moon. After that, it died down mainly cost. This is like, I think it's a huge, because they have proven these technologies that long back. It's not that it's not there, but the cost is humongous. And so you also need to pause and see. You can't keep going unless you know what next to do. So currently, it's a time when it's not just these two countries, but around the world there is an interest in going to the moon, and technology developments have been really phenomenal from those 70s. So, and the reason is different now, that really need some permanent settlement. So it will become like in Antarctic stations by the next many years. Where we share stations, right? India also has station in Antarctica. So it's a kind of permanent settlements. So,
Would you also like to say something about Artemis and India's involvement?
okay. Yeah, so Artemis missions is the next human exploration mission by NASA, and Artemis 3 I think will go in 25 or so, but they will carry man and woman to the moon. We have also signed the Artemis Accords, which sort of agrees to cooperate with them. So again, today it is certainly international cooperation is required to carry out such big missions. It's about money, about know-how, sharing know-how, and in all sense cooperating in terms of data, safety, do a lot of cooperation in that manner, leading around stations or tracking it, etc. And we are in a position where we are also have that technology to do it, but we will cooperate. That way we are in a better position to cooperate with other agencies. So we will also be looking forward to that.
We'll take one question from YouTube and come back to you. Also, people on YouTube, you're welcome to post your questions on the chat and I'll read them out. There's a question by Crafting World. I'll just take one of your questions, which is were there earlier missions that helped study the composition, texture, etc. of the moon soil before the Apollo missions, and therefore how did you know about the surface on the moon before Apollo 11 landed? How did we?
So you still could look at it just simply looking at it, the reflectance, the albedo. To give a simple example, the albedo is different, which first basically tells you the composition is different, and then if you look at it in the infrared, you can get signatures of what the composition is. So we did have a fair idea before that on what moon is made of. We knew things like there is no magnetic field of the moon, there is no atmosphere. So most of these things were done by before Apollo missions.
There's one more question online, then we'll come back to the audience. Again from the same person. Is it possible to understand more about ancient Earth from the rocks of the moon?
That's a very good question, and we think so. In fact, there was a discovery of Earth material on the moon. In one of those sample return mission, we had a piece of Earth because just like we get lunar meteorites early on, it's very much possible that things that have been by impacts thrown off into space could land on the moon as well. And as I said, this is a window to the early time of the solar system. So because moon and Earth, we at least believe, formed together and it's been at the same place in the solar system, whatever happened to moon must have happened on Earth as well. All the impacts that have happened earlier, that must have happened to Earth as well. So it all gets connected. The evolution of Earth very much follows what happened at the position of the moon as well. So yeah, we have a lot to learn on what happened in the early solar system.
Come back to the audience. Yeah. Mike.
Gravity assist. Yeah. You had a question about it? Yes. Come to the question. Yeah. While I move the slides here.
When I'm playing space like
But then you have to also spend more fuel, no? So there's delta V, right? How much velocity you should give it, right? So if you do that at one shot, you have to give higher velocity to it, which means you need to spend more fuel. So even with this, you are spending fuel. This burn here, that is what is raising the orbit. So if you want to raise it directly from here, you have to give that at one shot, which will lead us to spend more fuel. If you want to conserve it, only the least minimum fuel you want to spend. Try that in your simulation.
What's the name of the game you play?
Space flight simulator.
Space Flight Simulator for people online. Do try it. Yeah. Other questions? Yeah, please.
Ma'am, whenever any satellite which goes to the moon follows this elliptical orbit, doesn't it like go through a series of space jump? Doesn't it get affected by the space jump before it reaches the moon? Like how is it avoided?
Right. So it's getting more and more a problem these days. If you look at the space debris around Earth, that's quite high, and the chance of collision becomes higher and higher. There is shielding on spacecrafts to avoid, but rare cases you do get hit. So it's like today we are having more and more shielding mechanisms to make sure such large damages don't happen. That's all you can do. And now when there are policies that are being built up to make sure these spacecrafts are brought down, at least in future we don't pollute it more. But as of now, yes, there's a lot of debris and there's a real concern. That is also there, and bringing back the satellite, like you keep enough fuel so that the end of life you pull it back.
In fact, I think ISRO is building a
Right.
series of telescopes to monitor them, and one of them will be in Hanle.
There's a series of telescopes called Lunar.
Other question? Yeah, please. Please wait for no? Oh yeah, okay, there we go.
So what exactly are lunar meteorites, and like how do we get them?
So it's a meteorite is something that you get, that's an extraterrestrial material that you get on the surface of the Earth. We know it's lunar, basically if you look at its isotopic ratios, so if you test it for its composition and isotopic ratio, you know it's lunar. But even we could say something, or a meteorite is lunar only after Apollo missions, when you had very precise data. So it's a meteorite, and we say it's from the moon by comparing this from our understanding of how moon rocks are.
So it like comes from the moon, like
Yeah,
breaks off
right.
from the moon.
Not just now. It may not be that it was ejected now. It may be something that was ejected billions of years ago and has been going around in the sun's orbit. And because these are small objects, easily gets perturbed from their trajectories and might have come to Earth. But if it comes near, it will be pulled back.
In fact, I think when I was in school, there was a news article that they discovered a rock in Antarctica, which they claimed came from Mars.
Yeah. So there are a set of meteorites called SNC meteorites, which are we believe are from Mars.
Yeah, there was a question. You had a question. Then.
I had come across an article claiming that to reduce the temperature on the Earth or reduce the harmful effects on the soil, in case if there are flare-ups, they are going to bombard lunar phases and create dust so that it creates the shield. So because this question is arising dynamically because of the effect that it will have in the later lunar, whatever, the Chandrayaan, whatever, lunar missions or any other missions if it gets escaped from the environment of the moon and comes into space. It was something which we don't understand.
Okay, I have not read this article, but probably it's a proposal to, as one of the ways to shield it from it.
The solar flares, in case if there are.
Okay, there's plenty of material from the sun, surely, but shielding it like this is probably a huge effort, and I really don't know about it.
You had a question?
Actually, moon don't have volcanoes.
Yeah, it doesn't have volcanoes.
Then how can they have lava?
So that's a very good question. Yeah, so it's not having volcanoes like on Earth. You know how Earth volcanoes are, right? But these lava is because of big impacts. So it's like such a big rock came and hit and made a very big crater. You know crater, right? Because it was so big a hit, there's also there's so much of heat that the entire rock and the surroundings fissures or cracks in the surface, from interior molten lava comes out. So that's the kind of volcanism we are talking about.
Yeah, here, the person there, and then the back. No, sorry, the person there, the blue? Yeah. Oh, doesn't matter, yeah, please.
If I have heard correctly, you talked about the water on the moon formed because of some reaction. So, is there hydrogen for the formation of water? Definitely we write hydrogen and oxygen. So, does it mean the hydrogen and oxygen is there in the environment?
Yes, yes.
So that means moon has, although little, but it has some sort of environment. Is it?
It's not the environment, it's on the grains itself. In fact, the surface of the moon, it's all oxides. So there's like 45% of oxygen in the soil, and hydrogen comes from the sun. Now imagine when there's always hydrogen coming from the sun as it was in, like last billions of years, it's getting implanted on the surface of the moon. So there is a lot of hydrogen. So this is, but the water on the moon is something very dynamic process. So this reaction, this is a source, let's say, which forms this OH bond and makes H2O, not inside minerals, but just as absorbed on the surface. Just like, not even like a sponge, but something which is not inside the crystal, but just sticking to it with weak ionic bonds.
That means some reaction is happening
On the
which is
surface,
breaking that oxide thing and
what is on the, there are oxygen also ions coming from the sun.
yeah.
So there's a particular reaction which, I don't remember the reaction itself, but basically solar wind interacts with that surface material, and there is oxygen on the surface as well as from the sun, and this particular reaction. We know this because if you look at times when moon goes through the full moon, when solar wind is stopped, you see that there is some data which suggests it lowers there. So there's some evidence to say this is a solar wind mediated.
So if we would be able to properly analyze that reaction and do something for that, so will there be a possibility that we
Make
actually
water.
create water?
Yeah, right. Yeah, that's true. It's just that it's a huge flux there, so the scale of things are different probably. But yes,
Thank you so much.
So what we've seen are basically molecules form
on the surface.
instantaneously on surface rather than like a puddle.
Right. It's not at all that.
What I have thought earlier actually before
Yeah.
this lecture.
It'd be nice to have puddles, but clearly that's not it. Not it there. Yeah, you and then we both go back.
So we saw that the moon is moving away like 3.8 centimeters a year. So will there be a point at which we can start seeing the far side of the moon, like it stops being tightly down?
No. So this is basically angular momentum transfer. So as you move, okay, in the sense that our Earth will start spinning slower, and the rate of rotation in both cases will change.
Yes.
Yeah, right. But yeah.
Hypothetically will be.
Yeah, hypothetically.
Yes.
Just that is a long time scale.
Right.
So the question is that.
Yeah, I'm a bit more from the social science field. So I've always been wondering with all this kind of space missions and lunar missions. It's often also like about prestige for a country. It also develops military and stuff. And we're facing a lot of problems in this world. There's climate change, there's a lot of wars, there's poverty. And from a social perspective, I've always been wondering, like, are such kind of programs, are they justified? Are they benefiting us as a human species in the short term as well as the long term? That's like a more general question.
Yeah, I understand. I mean, this is something that you always ask yourself as well, right? Particularly when you are in space sciences, and you feel like first look it doesn't seem to connect with what's right there today. But from a larger perspective, as you yourself said, the improvement in technology that comes from this, it really gets to the point when you do breakthrough technologies, which has several spin-offs. In fact, the pacemaker, they say it was invented from the Apollo programs. There's a huge amount of technological improvement that comes from such programs, which has spin-offs into the society. And particularly in the case of India, as we said in the beginning, the space program itself was envisaged for people. And this is a very small part of those. Still we sent in a year tens of satellites for, yesterday there was a launch, no, which was for Earth observation. Communication, and everything that you use your mobile phones on, telemedicine, the urban planning that the government does for the defense purposes. There's a 90% of this is actually social. This is a very small part of it. And science progress and fundamental science or astronomy is very much part of that larger understanding of fundamental human knowledge. And in fact, we are actually spending a very small part of that, particularly in India, for space science research. So that way, I think we have to do this. It's not really a major chunk of it that is being done. We need to do more, but at least it's not really eating away the rest of it. I mean, it is like, just to say that, because, do you think poverty will stop if we stop our space program? It's not like that, right? It's all planned in a way that the amount that we partition to these kind of programs are also important for the progress and for the future of our generations. So I believe it's just a fundamental physics.
Can I add to that?
Yeah, sure.
So there's somebody who keeps talking about outreach all the time. So I think it's a larger question as to why a space program, why do you want to go to the moon at all, right? So the initial race to the moon might have been inspired partly by geopolitical reasons, but then like the speaker said, there are the fraction of cost in this is actually a small, very very small compared to the space program itself for social or societal benefit, let alone compared to the what my takes to make a Bollywood movie, right? Which is like 10 times more. But then another technology spin-offs. I would say spin-offs with technology or byproducts which are very very useful, which come out of the space program. That's one thing. But let's not also underestimate the fact the impact space programs have. Just like the impact music has on culture, just like the impact of films have on culture, painting has on culture, dance has on culture. These things, science also has an impact on society. Otherwise, you would all be here on a Saturday. You would be out seeing a movie. Right? The fact that you're all here tells you there is something about going to space that excites us, that brings us together, that makes us want to know more about something. And if you're here last year on August 23rd when Chandrayaan 3 landed, the palpable feeling of oneness, of unity, of something beyond ourselves we are a part of is unmistakable, right? After the Apollo mission, after the first, after Neil Armstrong landed on the moon and after the Apollo missions, there are studies which showed, for example, that the fraction of students opting for STEM as a career, physics or mathematics as a career, increased partly because they were inspired by the space program, by the Lunar, by the moon program, right? So these things can be partly intangible, partly tangible, but they make a huge difference. And if you remember the feeling on August 23rd last year, I don't know of any other instance where science or something which is beyond all of us has brought us together in that way. If we had 1,400 people, million people in the world, I think 600 million saw the landing, right? And it wasn't, you could do that for a cricket match, you could do it for Olympic Games, you could do it for something else, but it did it for science, it did it for something which is beyond ourselves, which is to land on a body you could see at night, right? I think that the intangible benefits of those are also valuable, along with the tangible technology spin-offs.
And perhaps space is the only thing that can bring the world together as humans. When we go to, you go out of Kerala and we are like, oh, okay, I'm from Kerala. And then you go out to US and somebody you meet on Indian, you're happy. So probably when you are on Mars or Moon,
you may go on Earth as well. Me too. But I think it's an important question. I think the answer was. Other questions? There was something from. Yeah, please.
Well, my question is about how did people landed on moon make up back? How did they come back to Earth, and what was the preparations made?
Oh, okay. This all basically it requires an ascent module. So you need also a launcher there, right? Just like you can't make this. We launch rockets from here, but their launch pad is created, and you have a ascent module. So basically that fires and you come up. So we said preparation. There were dozens of missions before that actual Apollo 11 landing. wherein various steps, this was all rehearsed perfectly well. So there were missions where first they went around the moon but did not land and came back. You know, they just get close and come back. Then robotically tried landing. So you know, the preparations that you have to do for a human mission is completely different from when it's a robotic. But you cannot afford to take any risk, right? That's what even today now if Artemis goes, that's what they're doing. So the US is sending initially uncrewed models. So that's the part that we have to take too. So I mean, it's really very complex, challenging because and again, one-time landing doesn't mean you will do this again, isn't it? Like every mission has its risks. And you know about Apollo 13, even though they did Apollo 11 and 12, when it came to 13, halfway through they encountered a problem and had to come back. Right? There's a famous movie on that. So that is one thing, being in ISRO, that I feel that every mission is taken seriously. Today we see that PSLV is something like a workhorse, and it's not that everybody sits around and says this is going to be fine. Every mission and everything that we do is given that due seriousness. Every little thing, imagine, it's like this is such a huge teamwork. It's like you are doing something, you can assure I am doing it right. But when it's like the 5,000 people involved in making a spacecraft like this, every screw that is turned has to be the right torque, for example. You turn it a little more and something might break. You know, so every test that's done, there's a huge number of tests done. Every test done has to be perfect, every data has to be analyzed. So it's like a big teamwork, and I think no other organization that I know of will such a big team come together with a single purpose. So that's what I love my job about. You know, because you say you need to have trust in your team. It's not like somebody is indispensable. You have engineers, you have a lot of people coming together to do a single thing. But everybody's work matters, isn't it? Every technician's work, everybody who is there, who's associated. Whole of ISRO is probably associated with Chandrayaan 3. It's not just about a small team doing things. So there are multiple factors that make such a success.
I think that deserves an applause by itself. Like I say, there is a second chance in space. Right? Except for our space telescope, we got multiple chances. Yeah, other questions, and we'll go back to the YouTube. Yeah. I her, please. Okay, mic is that is, if you give it to him, then we'll go.
Ma'am, Vita Williams is at the interesting space station right now, and we see that there are some health issues. Can you just explain what would happen and why is the delay and what would happen if it stays for too long?
I shouldn't be answering this like it's a different agency, and so I don't think I should be commenting on that.
But what they themselves say, they're confident that there's no issue for them staying for a few months more. That's what I say. And I think, you know, and it's not as if they're the only two people stuck there. There are other people anyway at the ISS, right? It's not that the only two people there. There are other people who have already been there, who are planned, and who are anyway living there for longer as planned. Just that these two people were supposed to come back in a week, but they're staying longer. But there are also other people staying for as long anyway. So I think we'll watch what happens. I think it's like I said, it's going to make for a good Bollywood movie very soon. The person there.
My question is regarding phenomenon. So, sir, we observe certain phenomena, like for example, blood moon or red moon. So, what causes that?
Okay. So that's just because while setting the amount of atmosphere that's in between the moon and us, when that's different, it's just how the moon's image appears. It's nothing to do with its actual size. Also, the distance between Earth and Moon slightly changes as it goes around. It's not a perfect circular orbit. So, depending on when that setting happens and how much of at what point it's at the horizon, the look changes. Atmosphere, yeah, that's why I said it depends on how much atmosphere layers are there. and what angle it is.
Yeah.
Hi, so my question was for a mission that is on an international scale like Chandrayaan 3, it's obviously several years in the making. There's a lot of planning that has to go into mass budget, what scientific instruments are selected to go on board the spacecraft, and also you have things like since the moon's gravitational field is not even, you have to choose how low the spacecraft can go, which affects your science return. So how is a mission this big planned out so that you get the most amount of scientific return, given that you only have a limited budget, and how orbital parameters are chosen? Yeah, that's my question.
Okay, so as you said, there's a system in ISRO from the time of its inception that includes various levels of reviews. So when there is say a proposal, let's just take Chandrayaan 1 also. Chandrayaan 1 in fact came from a bigger community of lunar scientists who said like, I think we should try and go to the moon because of these reasons. We want to do these scientific studies. At that time, then ISRO took up this challenge and started working out from the very scratch. Because nobody tells you this, right? Somebody might have done gravity assist as he was asking, but doesn't mean that they just tell you this is how you do it and go ahead and do it. When we are designing a mission with what we have, there is every option to make it, as you said, minimize the resources and do it in a very optimized way. So first thing probably what will happen is to look at a mission configuration. Like how should you plan the mission, the trajectory, if it's to the moon, what exactly, there are different ways, as I said, different ways you can reach the moon. So the different trajectories, the calculation, and then you will see what is the launch rocket that's available, what's our capability, and even the budget of it. So Mars we sent with the PSLV, which became a low budget thing. But this is GSLV Mark 3, Chandrayaan 3 needed that because the weight that it carries. So to do the science that you want, what kind of instrument should go in, or what kind of altitude or landing that you need, accordingly the size of the spacecraft will increase. That's why it's called a payload itself. You have to pay for the load. So seriously, so for the rocket, the satellite is the payload. So then you configure the mission, and according to the satellite, you have to see which rocket can carry from what we have. So that, and then ISRO has a very good system of reviews. So we have designed reviews at various levels, each subsystem, like the satellite has subsystems like the power system, the communication system, science, instruments. Each of them goes through very critical, rigorous reviews, and the designs are frozen only what you call by maybe like 3-4 years. For example, for a scientific payload, you might design it and go through a baseline design review. They'll tell you what things you might want to change. You work on this, and then you come back with a second level of review after a few years. So the development goes on for let's say typically 5 to 6 years, where you improve your design, you improve your concept. So it's a very rigorous system. So that system is in place. That's why such a big team works.
Let me take one question from YouTube. The question from Bharti Sendil Kumar was: is Earth a habitable planet partly because we have big moons? Interesting question.
Yeah. So we think so. It isn't a habitable zone, but one of the reasons, at least, that the tides, we believe that's why, because of the tides, is where the sea animals really came to the land. So at least for evolution of life on Earth, moon does seem to have played a role.
It's not something you learn in school. It's very interesting. Yeah, the person.
Recently in the news we saw that Captain Shubhanshu Shukla has done 2000 hours of flying. So if a child wants to become an astronaut and he is good in both physics and physical activity, which is more important, aerospace engineering or IAS pilot?
That's the hardest question.
Once you start the Gaganyaan program, how to be an astronaut is going to be the question.
Currently it's from the Air Force that it's been. I mean, in fact, all.
Private entities have also come in.
Yeah, so probably in future there could be changes. At least all the Apollo astronauts again were from such. Because it's also about your presence of mind, and you're trained in such a manner when you go to such disciplines. But I cannot say what will be in the future. Thank you.
Hi. So first of all, thank you for the very detailed talk. So my question is about the craters. Why do the majority of the craters look always circular? Because if I were to throw a rock straight down at sand, it will always be circular unless it's elliptical. And chances are that most meteors are always, thrown at an angle rather than right angles. So why do they always majority look circular?
Perfectly circular are not so much there. But one thing is that most of these meteorites are also in the ecliptic plane. So there is more chance of hitting actually in a low, 90-degree or near that. You imagine, like, all these meteorites and asteroids are also in the ecliptic plane, and so the moon's equator is what will mostly get hit. When there is indeed a latitudinal dependence to it, so when they are hit in that manner, it will all be more normal incidents. But all the craters on the moon are not definitely circular. There are angles.
While wait for the next question, Vikrant is going to show a video of something we did for the last 2 asteroid days of Captain, which is partly, and I think Kumar here has been a part of it. Yeah, the question there. Disha, I think. Okay, fine.
So, can you share those details of that extra heat of the moon that it requires? So can you please share some details of that?
To sustain the volcanism that you see. Is it?
Yeah, like when one slide you said that there is a problem that.
Right, young volcanism that you see.
So, like, what is the
what is the problem?
What's the actual problem? Like, did they calculate the cooling and did it come out to be less than what is?
So the cooling rate will show that you should have by now spent all your heat. That there cannot be any molten material as recent as 2000 million years ago, right? Because everything would have solidified. If there was still rocks that have solidified 2000 million years before, which means they were molten until that point, which means you have to give more heat to keep it molten. So one thing we do is, so the heat after the initial impact, the heat is coming from the radioactive elements on the moon, because that's the only thing by radioactive decay that can provide some energy, right? Because the impact is over, now there is no source, so only source is the radioactive elements. So we have an assessment of how much of radioactive material is there in the moon, but looks like we'll have to re-look at it. Also, it could be the different phase diagrams. You know phase diagrams, no? How the temperature and pressure varies before a solidification can happen. So that will also depend on what materials were there at that point. So there's a lot of parameters here that will decide when it will become a solid. Not just temperature, pressure, the initial composition, the in-between phases of the mineral that will form. So here, these multiple parameters, we had a diagram, but now this looks like you have to change that.
If you don't mind, we just show one video. So 30th June is celebrated as Asteroid Day, commemorated as Asteroid Day around the world every year. That's the anniversary of the famous Tunguska event in Siberia in 1930. So what we do every year is we call people here, we tell them about asteroids, and then we let them throw stones onto flour, atta, to simulate impact craters. I think Kumar has been here twice. We'll show you one of that. I think we'll go to answering some of your questions. So if you come here next 30th June, you can have fun doing this as well.
A literal hands-on activity.
So then they measure the how big the crater on the atta is as a function of how high they throw the stone from flour, maize corn flour. So if you see, it will tell you. So if you throw stones at various heights or various angles, how does that change the shape and the size of the crater formed in the flour? Right? So this will simulate what happens on the moon. So Kumar here has done that more than he's gone back fully white at the end of the day, much to his parents' slight disappointment. And right, so
See, that's the different parameters that they
so before that, we played around with Maida, Atta, various kinds of flour to see which gave good impact craters, and we chose corn flour. So this is something you can try at home. You can actually do a pretty good recreation, right? So you can vary the angle of impact, you can vary the height from which you throw, the velocity, the material, how much you pack the atta, right, before doing it, etc. And then you can measure the size and shape of the crater, craters formed, and you get nice craters just like on the moon. And then you have these craters, and then you find this atta thrown out, just like Bam mentioned from the Tycho crater, with these streaks thrown out. You can actually see them. You can do it yourself and check it out. It's quite good fun. Then you have to have a bath after that, right? Yeah, we'll go back to questions. But before we do, there's a sign-up sheet going around. If you haven't signed up, please do. Just sign in, and yeah, we'll go back to other questions. The person here, and then no, he's been waiting for some time. So yeah, let's go.
Considering just how inhospitable the moon's geography and climate, and atmosphere is, would long-term human habitation really be viable?
Yeah, we do need to have controlled environments. We're not talking about living there on the surface. We do need to create controlled environments. So yes, that's what we're doing. Controlled environments, I mean, where you have to keep your temperature, pressure, radiation shielding, dust protection.
I meant more about the economic viability of creating.
Or the cost factor. I think you should just calculate that.
Yeah, then.
As you told, you can get many answers from the moon about early universe. So can we get some evidences of magnetic monopoles from the moon?
Can you also tell me about the motivation behind the question?
I've been reading about this since 1.5 years, and I've been to read papers and all, but as you told, you can get many things, many answers from the moon itself. So I have that curiosity.
No, I can, first of all, okay, can you tell me how do you look for magnetic monopoles?
It's like what I have read was early universe. You in that high temperatures you can find us, but the contrast of that I have read in one Gostar's paper. He told we can find it in the coldest temperature as well, in plasma. So is there anything?
So moon doesn't have an inherent magnetic field. It's in nanotesla, but more coming from a shock related. That's what we think. So it's very weak magnetic fields, localized. There is no global magnetic field. I have no idea how you find the magnetic monopole.
Also, second question. As you are an inspiration to all of us as a women scientist, so can you tell about your journey to ISRO or motivation to physics?
Okay, so I basically studied in, I'm from Palakkad in Kerala. I studied my school and college there. So first thing, if that's a motivation, is to say that I have no idea. I didn't have any idea what a scientist is. You are all very lucky to have such a big exposure of things. I didn't know ISC existed. I didn't know IAA was there. I didn't have any idea of these things, and I said at the beginning I was more into English literature, and in 6th standard when my first short story came in Children's World, that was a magazine that we used to subscribe at that time. I was so happy that I thought I was really going to be a writer. So I had no idea. And then, as she was saying, I used to dance, and in fact in my school, if you ask, they know me more as a dancer than somebody who studies well. So it didn't really nothing to do with this. Perhaps until MSc, because we all come from areas where there is no such exposure. You don't get to hear talks with people, and just did. And I just took physics because my mother said to. So nothing else. So but MSc was more serious, and there are really, because we had extremely good professors. So one of the things is, for every child, I think the most important thing is to have a good teacher, because you like the subject. The best teacher, right? When you like the teacher, you like the subject. That's how always it is. And English teachers are always, I find, really nice because they tell you stories, they discuss stories. So I always loved English teachers. And even in college, my best, favorite teacher was an English professor. So until MSc, there was nothing serious. But when we got to the university for MSc, there were excellent teachers who made you understand what physics is about. And then I have to thank one of the professors who pushed me to do a summer project at IIA. So that was like going out first time to Bangalore, and in fact my parents agreed, which was a big thing. And I came here for 2 months, and that also changed a lot of things. I did with Professor Anupama using for supernovae. Everything was new. I didn't even know how to use a computer, but that was not the time when you had a lot of internet and computers. I think internet was just coming when I was in MSc. You have to go and book when you want to do a browsing. Can you imagine that? Even my son now, when he goes to Kerala, his first thing is, is there Wi-Fi there? Is it 5G? Only then I'm coming. So I being at, I have to say, I was a sort of motivation. I saw that there was a possibility of things like a PhD, because I never thought there was something that I can do. So I did a summer project, went back, finished MSc, and I got married. So I got married and came to Bangalore. And then I was looking for a job desperately. I worked in Presidency College in Hebbal here for 6 months as a lecturer. But that really helped at that time, though I didn't. Sort of because I was not teaching well, I think, and I was half the time crying, in fact, because I was just 22, and then the students were also like 17, 18, and they had fun with me probably. So I would end up, because I'm not able to make the class disciplined, it was half the time crying at home. But somehow persisted, but it really helped. So I believe in everything in life comes for a reason. That 6 months really improved my fundamentals, because I have to teach these music kids. So when I did an interview for ISRO as a JRF, I think I did pretty well. So that was again a turning point. And then the rest of this, all what happened at ISRO, got a chance to work on a mission like Chandrayaan, and had an excellent PhD supervisor. No, he's an absolutely great mentor. So basically, a PhD is something that somebody doesn't teach you. It is something to let you learn. So that kind of freedom. And then ISRO environment, though there are, you might say, we have restrictions entering. There's not so much of internet freedom that you have here. But the best thing I feel is, like from a PhD, you really have that feeling that something I had on my desk, I used my hands and touched it, and to imagine at the end of my PhD that is around the moon was something like, I can't describe that feeling, And then I already had my daughter by then. Actually, I did my PhD with my daughter. I did my coursework when she was 6 months old, so my father would come behind with me to ISC to do the coursework, and she would stand outside and so all that. So when this girl went up, she was like 2.5 or 3 years old, and I would say, I can push the button here and the door will open there, kind of, and she was like really impressed by that. So yeah, that's why I love being in ISRO. You get to really work on missions like this, and you really feel part of their joy, really experiencing it. As I was saying, Chandrayaan 3 also, being there and really seeing it go down was a great experience. So it's for that, I think all of you, it's not about you should come to do astronomy. The main point is that you should be able to do something that you love in your life. Imagine working for 40 years or 35 years and not doing something that you like. It's like most important part of your life. Don't you want to do something that you love to do? So whatever you take as your career, make sure you love this. So every Monday I go excited to the office. Not that it's a Monday I have to go, right? So make sure you do that. That's all.
Excellent. So thank you so much for the question. I think it's a great question. We can talk about the science and technology, but then I think it's important to talk about our journeys as well. It's also important to make sure that science and technology is accessible to everybody of all backgrounds and diversities. For example, the Astronomical Society of India, the ASI, has something called the Working Group for Gender Equity, which works towards promoting gender equity and diversity and in astronomy in India as well. And I think she talked not only about talk about gender but also about backgrounds, where you come from. Astronomers should reflect the country, right? And therefore it's important that we make sure that the scientists also reflect the country, everybody in the country. I think that's very important. So I'm very happy that you were able to address the question. Going back to the moon, from Earth, other questions? Yeah, you'll be waiting for that. That will go.
Since the craters are created on the moon because of the asteroids hitting the surface, so why are there so many circular craters in the south pole of the moon?
So it's hitting from all sides. What I meant was, to get it circular, you have to be in the same plane. But actually, if you really look at the diameters, not all craters are really circular, but it's uniformly hitting. It's not like only craters are. Yeah, it's uniform.
So basically my question is that from Earth to the moon, like you transfer data from the photos, but there's no signals in the moon. How do you transfer data and virtually communicate it?
Radio, right?
Yeah, radio, but how is who invented and how is it invented?
So just like how you communicate here, so there are these bands, S band, X band, that you particular frequencies that you use, which has to. So on Earth also there are definite bands, no, for communication. Definitely to the moon also. Therefore, we use S band for communication, for example. That particular set of frequencies work. Yes, it's all radio communication.
And my second question is that we have mostly seen the auras from the magnetic lens, they're blue and green, right? But I have seen in the picture it's very bright red. Can you explain what happened like that?
In Aurora?
Yeah. Yeah.
Oh, why is it red here?
Yeah.
Oh, okay. This is probably lower in atmosphere. I don't remember. So its oxygen is red, nitrogen is blue. Yeah, I don't remember the colors. So probably oxygen is red. The green is nitrogen, I think. You have to look it up. Yeah, Neeraj is answering that.
Thank you.
Thank you for your question. My question is regarding helium mining. What is the current status and what is the interest level in
Yes.
useful or
So helium cannot be directly mapped. So all this talk about yeah. So first thing is to see. First step to mining is mapping helium-3, to know what is the quantity available. All our see, helium-3 is coming from sun. There is no production of helium-3 on the moon. So what we are thinking is, if you calculate from the beginning, solar wind is falling on the sun, you can calculate 4 billion years how much helium-3 is there. That is the most way people are saying there is helium-3. One of the Chinese spacecrafts have an indirectly mapped helium-3, and we think it is there. So it's one of the materials you can extract and use, because helium-3 is very expensive on Earth and has variety of uses. There are methods that are being tested on ground to extract. For most methods, efficiency is not good enough, economically viable thing, as somebody was saying. So the process-wise, there is an improvement in research, but to actually do it on the moon, we have not done so far. Nobody has done so far.
is there any current interest?
Yes. Helium-3 is certainly of interest. It's more on the moon than Earth. So.
After this, we'll take 2 more, then we'll
Yeah, so my question is, so my question was, on the far side of the moon we have more craters than the near side. Is that because of tidal locking, or what are the other theories that can explain that?
Number of craters wise, I don't. Just that that is an older terrain.
Yeah.
It's an older terrain. Because here you see the mare has resurfaced from interior. So that's wiped out some number of craters.
So why is that not happening on the far side?
So we think, we find that the crust is thicker on the far side. Why is that is not known, but at least that.
Hello. We know that moon is a type of satellite, right? Natural satellite. So how do we define a satellite?
When it goes around with a common center of mass, for when there is some number, so many years, like that's why the Phobos Deimos won't, and its trajectory is changing. When it's coming closer, so that's why we wouldn't define it in the term of a natural satellite.
But then even the planets revolve around the star and the stars revolve around the
Yeah. So that's, we just termed it a planet. Right? So as a body, it is the same thing. Like this is going around the common center of mass. So as an object, class of objects, moon is differentiated. So if you keep moon at some other place, it will be called a planet. In that sense, it doesn't have any difference.
So we don't call it as a moon. Maybe something like that.
No, because it's revolving around Earth, we are calling it a satellite. As an independent body, it is like a planet. Whereas asteroid is not, right? It's irregular shaped. It is not differentiated into crust, mantle, core. So there's a difference there. But this is a class. As a class of object, it is like any terrestrial rocky planet.
But then the L1 and Voyager 1 and 2, even those are satellites. So how do we term in general?
Which ones?
Aditya L1 and Voyager.
Oh no, that is an artificial, right?
Yeah, but all of these are satellites, right? So
Yeah.
how do we generally term, or define as?
This is a naturally made, isn't it? Yeah, it's a.
We just know that it is a natural.
It is a natural satellite. It's definitely not something we have artificially kept there. Right?
Thank you.
I think we have to stop. Okay, very last question, and then we stop.
Yeah, a similar question to what he said. Like, what exactly identifies as a moon? Because, like, for example, for Mars, Phobos and Deimos, they can be considered any extraordinary orbit. Same with Saturn's, many of Saturn's moons. Then why do we label them as moons?
So again, as I said, it's a more to do with the terminology. Our case is very special because it's formed at the same time, and if you look at the common center of mass and the trajectory and how the trajectory has evolved, it's something that formed here at the same time as Earth. Like it's a twin planet.
I'm not talking about Earth's moon specifically, like any moon. Like, for example, Saturn's moon, like the largest moon of Saturn, you can call it a moon. Like it has similar dimensions to the moon we have on Earth. It's a similar satellite. But then for small asteroids, which we randomly can label as moons, why do we use it?
Because it's an asteroid. They are not spherical. They said it's not like a differentiated body. It's irregularly shaped.
No, but sometimes they label those in moons also. Like for example, Deimos is exactly not a circular object. It's still considered a moon.
So moon is something used to say like in place of saying a satellite, you call it a moon or something. But what is that class of object if you look at it? Phobos and Deimos are asteroids.
So there's no clear definition to what a moon is?
Moon is something that goes around the orbit of this planet. But as a class of object, it's an asteroid.
Okay, somewhat clear, sir.
I think we'll stop here. It's 6:30. And I think we all been here for a long time. But I think we should before I conclude, I'd say a few things. One is there's a QR code to join the WhatsApp group we have. This will tell you all the public events we organize. So now's the time to take your phones out and then join the WhatsApp group. Only I can post, so none of you can say good morning to each other. It's also stuck outside. There's also another QR code stuck outside with a small feedback form you can fill up online, which asks you not just about whether you had fun today, but also asks you how you came to know about the event, etc. So it helps us plan future events as well. 23rd August is National Space Day, so what we're going to do on 23rd August in the afternoon will be a special public talk by Dr. S. Sita, who's at the Raman Research Institute, and she used to be the Space Science Program Office Director at ISRO. She's going to give a talk about astronomy done with various space missions in India since the very beginning. So I do urge you to come for that. We'll put out a notice on this WhatsApp group about that. In the morning on the 23rd, we're going to have a special quiz for 10th, 11th, and maybe 9th standard students. We allow one team of 2 per school, so we do urge you to kind of sign up with him about that as well. Once the sky clears after the monsoons, we will have nights where we put telescopes out and you can come and see the moon. So we do urge you to keep an eye on the WhatsApp group. We've done 3 or 4 in the past, and we continue to do so starting October. And I think how many of you see the moon by the way through a telescope? Oh, that's not bad. That's very good. Shyama, please take a look at how many people see the moon through a telescope. That's a good number. How many of you see the moon through a telescope from here? Okay, so it's special. So we have special things we add on to the moon observing sessions here. So do look out for that as well. You might have noticed that it's very hot the last few days, right? Why do you think that is? Also, why only last few days? There's an astronomy answer to my question. What is it? There's something happening tomorrow in Bangalore. We're not doing an event here because it's going to be raining, but tomorrow is zero shadow day for Bangalore. Do you know what it is? We had one in April, right? So tomorrow, during Dakshinayana, when the sun moves from north to south, tomorrow sun will be exactly overhead Bangalore at local noon at 12:20. Okay, and that's also why it's a bit more hot these days because sun is exactly overhead, so there's more light coming per unit area, right? So if the sky is clear, go to your terrace and you can put some vertical pipe or some object, and you can see at 12:20 the shadow exactly disappears to the thing. You can try out. We do have public event here during the Uttarayanas at zero shadow day because we know sky is clear. Tomorrow it's iffy, so we're not going to do that. Yeah. Exactly. And so the Dakshinayana zero shadow day for Bangalore is tomorrow, right? And like I said, come on 30th June, you can throw rocks at flowers, but then let's conclude by thanking Dr. Shyama Narendranath again for a wonderful talk. I think he's made us all like those who will say you made us into professional lunatics now. We all like the moon a lot. We'll be organizing more events around the moon, around other astronomy phenomenon events in the future. So please join us. Let your friends know, and we welcome you back again next time. And with that, let's thank her again. She'll be here for another 5-10 minutes, so you can quickly come and have a chat with her if you want to. Yeah. And if you haven't signed up your name, then just sign up on the sheet if you like. It's not compulsory, but please do. We can stop the live streaming. Thanks again for people who joined online on YouTube.